Welcome after the lunch break to Kaleidoscope of Lambdas. My name is Dawid Zalewski, and it's not the first time I'm talking about Lambdas, so it's around fifth time. So I might be going too fast sometimes. Please stop me if I'm going too fast. Also, if you have a nagging question during the talk, just interrupt me because I'd prefer that you leave this room well informed than I finish on time. I mean, I want to finish on time, obviously, but if I skip last couple of slides and still to your advantage because you understand something better, I think it's just going to work out much better like this. This talk is basically a fundamentals talk. So we have this kind of hidden fundamentals track at CPP on C this year. And it doesn't go very deep, but it goes very broad. And we will stop somewhere at the upper intermediate level. And I do assume that you have seen a lambda in your life, right? Or you have written one, and that you more or less know what it is. So I'm not going like with explanation of every basics. This talk has roughly this flow, roughly because actually there are 6 different points, but I only could find a picture with 5 different points. So that's how it looks like this. So we're going to talk about why lambdas at all, why they were introduced to C++, because the motivation behind the lambdas is very important in understanding their limitations, especially their initial limitations. And many of you are still on C++, 14, 17, these kind of versions of languages, and they are really limited to that. Then we're going to talk about what a lambda really is, what you get when you write a lambda expression, a little about the evolution of lambdas, so how some features came to being, but the evolution is combined together with applications, obviously. Later on, we are going to switch to applications, and in the middle, between 3 and 4, there will be a bit talk about capturing. So that's the point that didn't fit. At the end, we are going to go a little bit beyond the basics. So let's start with the tale of colors. I mean, that's how the lambdas came to being way before 2011 when they were first introduced to the language. Like many people used to write this kind of code when they had some structure, whatever it was, some piece of data, and they needed to do operations on it. Like, for example, filtering based on the saturation or whatever it was. You had a collection, you put it in, you wanted another collection out. And that used to be the code that you would write a long time ago, right? And obviously this is really bad. So because you quickly realize, well, that's a very limited function. So I want something more generic. So the natural way of doing it is coming up with some filtering. So you would come up maybe with a filtering criteria, write a specific function that could use filters. From that on, there is only one more step forward to jumping onto predicate. And a predicate is simply a function that takes an object and returns a Boolean true or false, whether this object meets a certain criteria or not. And this could be, applied to some more generic filtering. So all of a sudden, instead of predefining within the function, within the filtering function, how we want to filter, we can put this work or we can abstract away this kind of behavior into a different piece of code. That's great. That's what we want. That only makes for more generic code. I mean, of course, nobody uses function pointers in C++ unless we are using them. We use function objects, right? So we will use objects that have the function call operator or operator parents implemented and that we can use as a function. This allows for such a beautiful generic code, right? We can put a predicate or whatever function, actually, whatever it is. It can be something that manipulates an object. It doesn't have to just return true or false. But in this case, since we are filtering a collection of colors, we are using a predicate. And we can kind of build all kind of functionality into this predicate, making our code super generic. And, from this one, from writing such a function that uses a predicate, which is a function object. So basically, when you already have this is only one step to a lambda expression, right? Because it's only natural then, instead of writing something predefined predicate object, which maybe you will use 3 times in your life, just write a lambda expression that does exactly the same, that you see directly what it does. You don't have to browse through your code base to find out what the hell this funny function is doing there. more maintainable, more readable, especially for short functions. Why would you create a whole new object for it? And obviously, when you are already using Lambda expressions, you don't want to also write your functions manually, right? You will directly go into algorithm and using a proper filter function, which is called copyIf in C++, and that's exactly what the loop was doing. Or if you are on a very modern language version, you would use ranges for it, which also work super nicely with lambda expressions. And this is actually where lambdas are in the language. When many years ago, around 2009, first papers, like formal papers, really flooded the committee with not really yet proposals for lambdas, but with ideas about lambdas. The main motivation behind the lambdas was to serve as actions for the STL algorithms, for all these functions that are in the algorithm header. They were meant to be used there, and that's why they came with lots of limitations, which we are going to talk about in a moment. So many things weren't possible even before. There were simple actions for algos. So this is the motivation. So what is a lambda? I mean, lambda is basically three different brackets, one after another, is in a very specific order, right? You have square brackets, normal brackets, and curly braces. This is almost the simplest lambda, because nowadays you can write also something like this, and this is also a lambda if you don't take any parameters. So, 4 characters already are a full lambda expression. More formally, if you really look into the standard, that's much, much more. Lambdas have kind of blown out of proportions when it comes to what you can put around them and inside them. They all start with a pair of square brackets. That's necessary. That's the lambda introducer. That's how the parser knows a lambda begins. But then already, if you're on C++20, you can put template parameters, explicit template parameters. Then they come lambda parameters that can be omitted if your lambda doesn't take anything. So you can totally skip this normal parentheses. Specifiers like mutable, const eval, static, const expr, no except. All of those go there. I couldn't fit it here because the width is not that great, right? But there are also requires. You can put requires expressions there and requirements and your concepts there next to the mutable. Finally, we have the compound statement or the body of the lambda. So it's a lot. And those expressions can become very, very lot, but that's because they hide a lot of power behind them, especially nowadays. Like, when you write a simple lambda, the compiler doesn't see a lambda, right? It's in the name. A lambda is an expression. So a lambda itself returns something, like all the expressions return something, and a lambda, when you write it, returns a closure object. So it returns an object of some closure type that's basically defined by your compiler what it is. What we know about it, it's a class type, and it has a function call operator inside. So it's a function object with the body basically exactly the same as your lambda expression. It also has a couple of other things, but in its simplest form, it might look like this. It doesn't have to, but this is how we imagine, how we like to imagine when we read how it should be, closure type might look like. So you get an instance of something like this back when you create a lambda, when you write a lambda. A function call operator, constructor, a default constructor, if you're on a recent version, if not, not really. And that's pretty much all. So when you run your lambda, so when you call it, what really gets called under the hood is the function call operator of the lambda itself. Lambdas come with many, many more perks. Like, for example, very commonly used one is the fact that you can convert a lambda into a function pointer. And this conversion is there. It's implicit if you want to do it. And it's thanks to a built-in conversion to a function pointer. There is an operator in every single or almost every single lambda inside that gets called to convert your lambda expression into a function pointer. So there is some static function inside and so on and so on. Lambdas can also use things that are around them, but there are different things or different objects that surround lambdas. Like, first of all, you might want to use in your lambda, within your lambda, an object with a static lifetime. So something defined at the global level or with the keyword static. Such things you can use out of the box, right? You don't need to do anything with them. They're always available, always within the lifetime. You don't need to do anything about it. They're there. If it's an object with automatic lifetime, so basically your local variables, you need to capture it. Because if you write code like this, with this n there, it's not going to work, sorry. You're going to get an error. You need to capture it. So you capture it by writing it in this lambda introducer called also simply a capture list. And this is capture by copy. I'm basically copying n into my lambda. When you capture something, it comes with very unfortunate side effects. You cannot anymore convert it to that function pointer, so all this functionality goes away. What does come back, or what you get instead, is the fact that your closure now has something akin of a data member inside. It's not really there, it's unspecified whether it's really there and what the layout is, but you can imagine it's there. And you can refer to it through the same name as you gave it when you were capturing it. Actually, we didn't give any name. We didn't give any name here. It's just n, but you can refer to it through n. There's also like a constructor, but it's not really there. You cannot use it, but we can imagine there is a constructor that takes also an integer and initializes it. So that's our closure object. With a capture, we obviously can capture pretty much everything, right? So you don't have to capture a simple integer. You can capture a complex object, like here, there's an answer provider that, for reasons quite obvious, has an implicit conversion to an integer with a value 42. So you can capture it, answer provider, whose implementation looks pretty much like this, and your closure object will reflect it. So there will be some data member maybe, but something that looks like a data member, answer provider, and you will be able to access it, except that this code won't compile, right? When you try to really run it, and it should basically emit this code where we call the operator int inside our function call operator. What we get instead is something like that. A very common error, and especially when you write a lot of generic code, a more complex code, sometimes it hits you as a surprise, like without any warning. And usually the most common reason for it is always the same, and it's hidden there, of course, in the error message, passing const answer provider as this argument discards qualifiers. So basically we ruined our const correctness somewhere on the way. Now the ruining here is actually very straightforward. Lambdas or closures have their defaults correct, and that's what people have been complaining for years already, that in C++ member functions are non-const by default, lambdas are const by default, or the function call operator of a lambda is constant by default. So that's pretty much our problem, right? One is constant, that one, but the function that we are using internally or in the lambda calls a non-constant function or on a possible data member. And that's a no-go. You cannot combine those two. And at this moment, you have two solutions. You either add the keyword mutable, the lambda, to basically express your idea that this lambda can mutate its members or the captured objects, and the const disappears, and we are all good. Or the other option, if you, for some reasons, dislike this solution, is to capture by reference. Because once you capture by reference, all your problems with constness disappear. You can mutate objects that you only refer to from your lambda. That's not a problem. It's an ugly solution, but it will work, right? It's the same with pointers, right? If you have a pointer in your class, it's not yours really what it points to, so you can mutate it. The same with references. So that's a solution. So those are lambdas like in a quarter. That's basically all you have to know about lambdas, about closures objects on a very high level of understanding and how they work, because there are lots of details when it comes to what functions are there, what aren't, what you can do with lambdas, but it doesn't really matter if you're just using them. There is one more ugly side to the lambdas, and people have been burned through it by it thousands of times. And this is that two lambdas are never the same. Even if they look the same, even if they're, syntactically the same, they are different objects. Every single lambda expression that you write gives a rise to a different closure object. So with a different name, only known to the compiler. So if you do even like a simple static assert on those two, you will get, well, it's not the same. Different objects, despite the fact that they look exactly the same. There are solutions to this problem. None of them are good. It's basically the same problem that you always have when you have some kind of basically polymorphism, because that's what you want to do here, that two different objects behave in the same way. So none of them are good, most of them are ugly, but there are solutions to the problem. The most common one is just swapping your lambdas into the split function, and the kind of your problem is solved. So using the type erasure on your lambdas. So that's lambdas 101 and lambdas closures. Let's go on.
If you declare a lambda inside a function, does it have the same issue as this lambda unique? So like you call a function that includes a lambda, then you call that function again. Will it create two instances of different lambdas internally, or assuming you don't mark it as simple like static or like that?
So the question was whether if you have a lambda within a function and you call this function multiple times, do you have a different lambda every time you call the function, or is it a different time, or is it the same type? And the answer is it's always the same type, because that doesn't happen at runtime. A function gets generated at compile time, so the same type is generated. There is basically how you can trick a little the compiler into creating multiple lambdas they look a bit differently. For example, that have different captures. You can write a function that returns a lambda expression, and then have basically a lambda factory that has the same implementation, but at least has different captures or captures different values. So you can abuse or actually use this fact. Let's move forward to the fancy topic, a very short topic of the evolution of lambdas. Anybody still using C++11 here, or we are not that old? Luckily, because lambdas were very bad then. I mean, lambdas didn't have any functionality whatsoever in C++11. Even the type deduction, the return type deduction didn't work properly, or it only worked when you had one return statement within a lambda. Even if two return statements were returning the same type, officially the type deduction broke. So that was really bad. And you could do very little with those lambdas. So there were no generic types, for example, which was also very bad because, standard algorithms are all generic algorithms, and all of a sudden you had to write lambdas that were not so generic. You cannot capture move-only objects, which was an omission, right? The unique pointer came with C++11 and no capturing of move-only object. And so on and so on. And, there were many other bad things about those lambdas. Nevertheless, they were there. Very limited support. Many compilers actually allowed directly to do much more than the standard was allowing, just because of this fact. Like even basics, like what I said, capturing a unique pointer, or capturing for them, as a matter of fact, of the surrounding object by copy, wasn't possible. And that's a very common thing that you do. You have an object, you have a class. This class has a function, like in this example, a function, and you want to be able to talk to your surrounding objects, capturing it by copy, making a full copy of it. That wasn't possible. Almost all of those problems were solved in C++14, which was a big overhaul for lambdas. First of all, we got generics. Second of all, we got generalized captures. That's how they are called formally. Both generics and generalized captures start with G. I think that's why they named it like this. Nobody names them generic captures. People name them init captures. What are init captures about? Well, basically something like this. This is an init capture, right? Or a generalized capture. You don't have to, or you don't just capture something. You can capture with an initializer, and you can either capture something by copy or by reference. You have two options. What matters is you have an initializer. You can put anything you want there. Type deduction for captures, for generalized captures, works as if there was a keyword auto in front of it. So just like a placeholder type auto, that's how the type deduction works here, which is sometimes important, especially if your initializer is a reference and you don't capture by reference. So imagine that your initializer returns an L value reference or is an L value reference for whatever reasons. If you don't specify that you also capture by reference, you will capture a full copy of it. So this references doesn't propagate without type deduction. The same rules as which you are familiar with. What else can you do? Or actually, what can you do with generalized capture? So like, first of all, you can create things on the spot. You know, there wasn't an answer 42 before, but you can now create it. It comes into being just by the virtue of being in the capture list, and you gave it a name answer. You can rename variables or rename your captures. So you had something called ounce, now you name it answer string because it's more convenient for you. You can, something that wasn't possible before, capture by const reference, which is pretty cool. So you can make things constant that weren't constant before, just by casting the initializer to a constant. Or finally, and last but not least, you can capture move-only objects by just simply moving them into Lambda. So your Lambdas now will be able to hold an object that's inside them by doing a move construction of it. And last but not least, capturing of the surrounding object by copy has been added. This is big. For the matters that we'll discuss also later, but sometimes you just want to make a full copy of whatever object you are in, maybe because you want to hide some information, for example, right? Some implementation details, whatever it is. And you just need a copy. Now it's possible, at least with the init captures. Next big thing that came with those lambdas in C++14 is generic lambdas. Generic lambdas with the auto types. So you can specify auto whenever there is a parameter in the lambda, and then reuse these lambdas for multiple reasons or purposes, whatever you want. Now, the only problem is that auto comes with an ugly side effect. For each single auto keyword that comes in your parameter list, there's a template parameter. So if you have two auto variables, they will create two different template parameters in your function call operator, which means that when it comes to the deduction of those types later on, you cannot really or easily put restrictions on it. You cannot constrain it. And code like this, which maybe I wouldn't like to compile, does compile when I call a lambda with an integer and with a floating point number. Because, why not? Types are properly deduced, everything is fine. There are ways around it, and again, none of them are beautiful. This is, by the way, not a way around the problem, at least not in this case. It is in some examples. You can decal type the second or whatever parameter to whatever you deduced before. So now your second parameter is in a non-deducible context. It will be basically the same as T1. Here it doesn't help because we have automatic conversions. So my double gets converted to an integer and still maybe it doesn't work as it should. But it could work in many, many other examples, right? So that's one of the ways out of it. One important thing that has been added to C++14 is parameter packs that can finally appear in the in the arguments list, and that's also kind of usable because parameter packs are getting bigger and bigger. So finally, you can write your lambdas that takes multiple arguments and forward those arguments somewhere else. Like in this case, just push them all into the vector by expanding or folding over a comma in an expression, and that's sometimes nice. And we'll use this fact later on when we talk about a bit more advanced applications. So C++17 came, and C++17 didn't have a lot of to offer, I must say. I mean, there are two different things that came with it. First of all, you could finally just capture the surrounding object by copy without any init captures, anything else. You just do asterisk this in your capture list, and your surrounding object gets copied into the lambda. And you can refer to it wherever you want. So you can get either the capture by reference by doing this, which was there since the very beginning of lambdas, or the asterisk lambda, asterisk this to capture by copy. The next one, and this one is pretty big, only in C++17, lambdas became cons expr. Before, there weren't any cons expr lambdas. And they are cons expr by default. So again, if, it's the same as with any other functions, normal functions or member functions are not by default cons expr, they are in lambdas. As long as your lambda expression meets all the requirements for cons expr-ness, it will be cons expr. So you don't even have to specify it, because it's like automatically there, or your function call operator is automatically cons expr, and my static assert here passes because it's an implicit cons expr. C++20, that's like maintenance, basically. Lambdas are slowly anyway getting into the maintenance if it wasn't for the explicit template parameters. So not a lot has happened when it comes to other things, but the explicit templates parameters are big. So we had this problem before, right? That we only could use the placeholder type auto, and that's bad because we can't really constrain our template parameters in an easy way. So code like this would compile. Now with C++20, it's all finally solved. We can just write the type name same, so you can specify the template parameter explicitly, and this code won't compile anymore because it doesn't get reduced to the same type. One gets reduced to an integer, one to a double. Doesn't work anymore. We get, not very clear message, but there is an error message, and you can maybe, deduce what's going on from it. What's even better, because C++20 also introduced concepts, we can use concepts to constrain our template parameters directly. And there are many different syntaxes to use it. Like you can do it like this. You can also put constraints on the auto if you want that. I didn't put it in the slide. Or you can write the requires clause if you want to constrain your same to be only the integral. In all those examples, you get very nice and clear messages, right? So good stuff. What else did C++20 bring? That one that's not yet there, but it's coming. And that's basically finally capturing parameter packs into Lambda by forwarding them. Doesn't always work as intended, and that has something to do with the type deduction, of course, of how type deduction of auto works in the capture list. But generally speaking, it works quite okay, much better than before. So before, what you could do, before C++20, if there was a parameter pack somewhere, you could capture it into the Lambda, but you could only capture it by copy or by reference, like the whole pack. But you couldn't really, move something if it was also passed by the error value reference into the make task in this example, or copy those that were passed as L values. Now it's possible with C++20, we can finally forward also parameter packs by capturing them. So forward them into Lambda. And that's very useful. That's very useful because it kind of replaces the use of tuples within the Lambda if you ever use tuples for storage. Now that's not really necessary, and you don't have to do a lot of gymnastics. It doesn't always work as intended or as you wish, but most of the time it does. So that's C++20, and it basically left only one hole in this whole lambda story. I know lambdas come from the world of functional programming, and functional programmers love recursion, right? So they like putting recursion wherever they want, and there are functional languages that don't have recursions, but they're very rare, and then you have to use combinators to fix this problem. C++, lambdas, no recursion whatsoever from the beginning. So you couldn't write something like this. You couldn't write a recursive sum lambda. A very simple reason. Sum is a lambda expression, so it kind of creates a whole object, right? A closure object. But when you write this lambda, so within this lambda expression, this closure object is not yet defined, so you cannot refer to it. That's impossible. So you're going to get this nice error that you cannot refer to a name of an object that's not yet fully defined. I mean, you could use something like this, and I'm not joking. A couple of years, it used to work on 2 compilers because of bugs, because this is not an allowed syntax. So you could, you know, knowing that there is a function call operator inside, you could directly call it, and it would have worked. But that's because of bugs, and you shouldn't really rely on the bugs in the compilers. Nowadays, luckily, it doesn't compile. Or you could just store everything into the function, but that's ugly. That's ugly, and that's not really what we want. Mostly because state function doesn't come without some hidden costs, at least of indirection, which is very often optimized away, but you might also need to maybe allocate on the heap, and you don't want to, right? So not really. There are many solutions to the problem. Like from the functional world, you can use combinators. From just straight on C++, you wrap a lambda within another lambda, and you're done. So our outer lambda is the lambda that the user sees. It's a sum lambda that takes a number, and the inner lambda does the whole implementation. It takes a generic argument as the first one. It's auto-solve. And we abuse the fact that it's there. And basically within the outer lambda, we call our implementation and pass the implementation to itself. So then it nicely can recurse. This kind of code usually doesn't look nice, right? People don't like seeing such things because, especially if there is mutual recursion involved and so on, that becomes very quickly very ugly. Luckily, with C++23, this problem has also been solved. So this is the only unsolved problem for lambdas, or at least one of the big unsolved problems of lambdas was that we couldn't self-refer to a lambda. Now it's possible. In C++23, we have the explicit object parameter added to our toolbox, and this comes with all kind of marvelous tricks. Basically, what it boils down to is, as you know, any member function in C++ has an implicit this pointer passed to it as the first argument, right? So now in C++23, you can specify it explicitly. And not only this, you can also make its type deducible and deduce not only the type, but also the value category of it and so on. For lambdas, it means that instead of writing this piece of ugly code, I can do something like this. This after removing all the everything that was before on the slide. So I can specify within the lambda expression an explicit object parameter, and it will refer or it will bind later to the lambda when I call it itself. So I can refer to myself again and again in the code. A pretty neat feature used for many other things also, but recursive lambdas are at least possible in this form. So that's recursion, and that's the evolution of lambdas. We still have 2 things to talk about. Important things. Capturing, a little about capturing, because capturing doesn't come without its own problems, and applications. So let's start with the capturing. There are many different ways to capture nowadays. Even if you only use the capture default and capturing this, that's like basically, your mind blows a little. And when you add to it generalized captures, it becomes even worse. So this is there to give you the whole, spread of different possibilities that you can use. What's important here is that in the beginning of C++, the standard wasn't really right. No, it was right, but they made a mistake when doing a standard. And the mistake was obviously in the good faith. But the issue is very easy. When you use capture defaults, doesn't matter whether it's by reference or by copy. So whether you request things that you capture to be referred to only or copied into your Lambda, the surrounding object, if you are in a class, always gets captured by reference. So you never ever get a full copy of it. This was fixed by removing it. So the second capture by reference, which is red, was deprecated. Nowadays, since C++20, when you capture by copy using the equality symbol, no more your surrounding object will be captured at all. You have to do it explicitly by saying how you want to capture it, either by reference or by copy using this or asterisk this. Why is it important? Because this leads to sometimes very ugly errors, and those errors are not always easy to detect. They're easy to detect, of course, when you use sanitizers and so on. But the more complex your code becomes, and the more nested lambdas you get in it, and nested, dependencies, the uglier it gets. Like in the simple one, we are still at the number 42, over-engineered checker for checking if a number is 42. We have an answer provider and the checker maker. And the checker maker is a pretty neat function because it uses two different lambdas. So one of them is basically, doing a difference of two numbers. And the other lambda, notice that it uses the AP, the answer provider, so it has to capture it. And it captures by reference. At least that's what it says there, right? There is a reference symbol, so it captures something by reference. And the other one, that's returned from the make checker or from the get function, is really the lambda that checks whether some number is within the tolerance to the number, distance to within the tolerance away from the number 42. Nothing more. It also uses a capture by reference. Now, this code obviously won't work, right? So you get an error, a runtime error, an ugly runtime error when you run it. And the problem is basically the same as in one of the talks today. You're returning a reference to a local object. You don't see it, but it's there. This is the tolerance. The tolerance is a local parameter, and we only captured it by reference when the function exited. It's not there anymore, and we're still using it. So you'll get a runtime error. Maybe not, if you're lucky, but the chances are you get. An easy fix, capture by copy, capture default by copy, and everything will work as a charm. At least it will work if we keep our code like this. So if this code is like this, those capture modes will work for this code. Now the situation will break drastically if all of a sudden the checker maker itself ceases to exist at some point that we used to generate the lambda. So even if you write one-liner like checker maker get for with the tolerance of 10%, it gets gone within this line. It's created. It's a temporary. You get the lambda checker maker is gone, and we get an error again. And you might think, if you're not aware of what those default captures mean, that the problem is the first capture. So instead of capturing by reference, you change it to capture by copy, because you think, well, the AP over there, which I'm using, is not being copied into the lambda. So let's make it equality. So now I capture AP by copy, and I don't have any problem anymore, right? And obviously, it's wrong. There is nothing like a capturing of AP. You cannot capture AP. It's impossible. AP belongs to your surrounding object. AP belongs to the checker maker. And you cannot just, cherry pick things out of it. You capture the whole object. you capture the whole checker maker. And since checker maker stopped to exist, and the capture default by copy captures the checker maker by reference, by default, and not by copy, you don't have it anymore. So a big surprise. And the surprise is especially in the fact that nothing in the syntax reveals the fact that you are not really capturing the surrounding object, or that you are, sorry, not really capturing the AP only. It looks like you are capturing AP, you are using it. Now, if you try to do it, if you try to capture AP in your capture list, you would get a very clear error, but here not. So the common advice is never to use capture defaults unless you are absolutely sure that you know what you're doing and that your Lambda won't outlive the scope where you use it. Like in this case, don't use the capture defaults, because this equality is basically exactly the same as if I did equality this, so capturing the surrounding object by reference, a simple fix, capture by copy, and it's done. And to be honest, very rarely you need the surrounding object like at its whole. It's much better to really cherry pick, but you can only cherry pick with init captures, with generalized captures. That's possible. Do it whenever you want. You will avoid lots of surprises, and you can just capture what you want. This won't even take any space. I mean, it's doesn't take any. I hope it doesn't take any memory in this case. So that's capturing. And now to the core of this business. Why would you ever use lambdas? Because that's what we want to know, right? Lambdas are used so much nowadays. Algorithms is a pretty obvious one, right? You would use lambdas in the algorithms with ranges. That's what they're made for, but is it the end of the day? Is it the end of the story? No, it's not. Lambdas are used in all the other places nowadays, and they're quite neat because they're expressive and because you can do things with them which are otherwise totally impossible, or at least not easily possible. Like a very common one, very commonly used one, is the so-called run once only lambdas, like this one. And the trick with those is to basically write your lambda and call it directly. This is calling your lambda directly after you write it is called an immediately invoked function expression or an immediately invoked lambda. You can recognize it by this, tiny little parent at the end of the lambda expression. You can see directly that I'm calling it. I'm calling it because I assign the result of it, and the result here doesn't matter. I'm returning a null pointer to a static variable defined somewhere, in this case, in the anonymous global namespace. Why it matters? Because such a thing will be only run once and not anymore. What's even more important, this thing will be run before your main function runs, right? So you can perform any kind of global initialization if you need to. Like in this case, it's basically disabling the link with the STVO. So I'm not syncing with the standard output stream anymore by my std_cout, which disables some double machinery that's under the hood and makes writes to std_cout much faster. Now, this is an ugly syntax, and people very often don't see this parenthesis. So instead of this, use standard invoke. It's there in the library. It's much cleaner. When you see standard invoke, you will know I'm invoking a lambda, and I'm assigning it to something. I have to assign it to something because otherwise it won't work, obviously. So that's one thing, global initialization before the main even starts. Another one, lambdas are marvelous when you need like a default function argument that's not trivial. Like in this case, I want to initialize number to something. It's non-trivial. I don't need to run any special function for it. I don't need to come up with anything else. I can just put it there, invoke it directly. A bit of an issue is that all of a sudden, my initializer is roughly 2 times as long as the whole function. But besides this, why not? This trick is much more commonly applied to initializing of data members. It very often happens that your data member uses a non-trivial initialization. It needs to check, you need to check some conditions first, maybe do something, and only then you can initialize. Like in this case, I have a token, I have the URI, and I have a task. And the problem with the task is that it can be only initialized after I do a couple of things. Like I have to make a connection, and only if this connection succeeds, I can create the task, right? So I have a special function start. Now the problem is I cannot write a member function, like a private member function that I could call in the task initializer, because officially it's not really legal to call your member functions before your object is fully constructed, right? So you cannot really do it. A solution is, of course, a lambda expression. You can basically put all this behavior into the lambda expression and you're good. And here I'm using a capture default by reference, not really contradicting what I said before. I said, if you're absolutely sure that your lambda would outlive the scope is defined in, that's not a problem. Here, it will definitely outlive the scope, or at least live as long as the scope. So I can use capture by reference and do all my setup there, even throw an exception. No problem whatsoever. A constructor is a perfect place to throw an exception if you like exceptions and want to signal that the construction failed. When it comes to initialization, you can also do any other marvelous things with lambdas. And this is basically, this should belong to the last part of my talk, but it's here. Lambdas became so flexible nowadays that you can basically put any functionality you want into them. For example, you can do some logging during the initialization, and you can do the logging in such a way that it's basically transparent to the object being constructed. Like here I have some object, it's a record object, and it can be constructed with a header or with a string and a hash, whatever it is. Well, instead of just passing the parameters there, like I would normally do, either the header or the ID and the hash, I call a special lambda there that logs those parameters and then initializes or returns an object. And surprisingly, that's a lambda expression. The whole log and init is also a lambda expression. It's a more advanced one. And I'm using a couple of features that have been added in the recent version of C++. Like, first and foremost, that's a variable template, right? So it's not really a variable. The log and init normally would be a variable. This is a variable template. I use it because I need to template the return type of this lambda. So what it really creates, what's the result of it. Then I'm capturing a lot of things. But before I do it, now let's talk in the order of all the slides. So I use it to return later on, when I created my return value, to create the object that I actually want to create. And it will be optimized away. There will be no move construction. So on this slide, when you go back here, when I return it, my head will be directly initialized from it without any moving or copying, because the return value optimization will kick in. So I will just directly return it. No problems whatsoever. No copies are being made. But what's important is how do I deal with logging? Because this is where the fun is, right? So to do the logging, I need two things. I need the name of what I'm initializing and the arguments I'm initializing with it. And the name is pretty easy. You just use the std_out and you put the name out. And then we have a parameter pack with all the names, all the values that I am using later on to initialize my object. That kind of expressions are very common, especially when you deal with lambdas that take parameter packs. This basically expands the parameter pack over a comma and sends each argument to the standard output stream with a little bit of comma symbol manipulation on the way. So I get a nice output, and there is no space after the last argument, or there are only commas after the arguments. But that's how you can do it. That's how you can do it nowadays. That's how you can do it when you finally have variable templates and lambdas that can take parameter packs properly. Explicit arguments are not necessary, but they definitely help. Initialization, another important topic. Initialization of constant variables, constant objects. So obviously this code won't compile, right? It cannot compile because my clock source or my clock is a constant unique pointer, and I cannot reassign it once I created it. And people have struggled a lot, or programmers have struggled a lot with constant initialization. This is a very commonly applied solution to these kind of problems, using the conditional expression and a conditional operator multiple times, nesting different conditions into it. Because it's it's an expression, so it evaluates to one thing. So I could use it like this, but this quickly becomes very ugly. It becomes super ugly when you have multiple nested conditions. So the solution is obviously using a lambda. Lambdas are perfect initializers. Just write your whole logic, whatever you want in it, immediately invoke it in your initializer, and your constant object gets initialized to what you wanted. Another thing, something that's been advocated since the beginning of the lambdas, they were also meant as a replacement of bind, including bind front, bind back, which were recently added to the library. For those of you who don't know what it is, a bind is a function in the standard library that allows you to bind some arguments to a callable. So you have a callable and you pass a couple of arguments to it, but not all of them. And you get a new callable that only requires the rest of the arguments that haven't been passed up till now, right? So that's what the bind does. So imagine I have like a serial channel with a simple function, right? Nothing special. I pass a span of bytes there and get state expected. And I want to use this serial channel as a writer to my debug probe somewhere. No problem. My debug probe expects a callable, which it can call only, so I can do it. I can create a serial channel and I can bind it, so the callable, to actually no arguments whatsoever, but I will create a new kind of a callable that expects one argument and directly pass it to the debug probe. So, the debug probe itself doesn't have to know that even there is a write function. It will work out of the box, no problem whatsoever. Now, the problem only begins when you add, for example, overloads to the serial channel, like that one. There is one single overload next to the original one, and all of a sudden binding becomes a nightmare. Anybody knows what you need to do then? Anybody ever work with binding? Now, what you need to do then is something like this. Because the overload resolution cannot really decide which write you want to bind. So which of those two write functions I want to bind, you have to specify it manually. And you specify it manually by casting the write function. So you have to cast it to the full type of it. This is beyond ugly and beyond long, right? If you use a lambda, that's kind of, that's all you need to write, right? So the overall resolution perfectly knows what you want to do. The same goes for cases when you get more than one argument, like 2 or 3 arguments, and you want to bind them in a specific way. So for example, you want to create a callable which has the second and the third arguments bound, but not the first one. This will explode directly. A lambda is much easier to understand and to write. And this brings us to the last part of this talk. Because we went through a lot of topics, what's really not really left is the cool stuff that you can do with lambdas. Lambdas nowadays are used, like I said, everywhere, and especially they are super powerful when it comes to expressing ideas from the functional world. And the functional world are, all the kind higher order functions that manipulate data, that check something, that maybe run multiple conditions on your data, or whatever they do. And those things are usually achieved by writing lambdas within lambdas within lambdas. So you cannot just go away with one lambda. Like, imagine something like this, a string validator. or a password validator in this case. And the password validator is a simple concept. It basically validates, whether your password is long enough, whether it contains the right characters, and nothing else. But you don't construct it manually. You construct it from lambdas, and each lambda validates a different piece of your password requirements, like the first one, the length, the second, whether you have numbers in it, and so on and so on. And it uses for it a special validated object, which is templated with string. So it will return a string or an optional of string for that matter. So you could use it like this. You could use it to validate a password, and then because it's an optional, you can do value or, so you will get either the validated password or an error, or you could use expected, set expected for it, whatever you want. Now, don't be surprised, but validated is a lambda, or to be like fully correct, it's a lambda within a lambda, only two lambdas this time. And they begin very simple, right? Lambda, another lambda. First of all, notice that my lambda there is templated. So I do validated of string. And to achieve this, you again have to use the variable templates because there is no other way to template a lambda itself. So there is a variable template, my return value. Now, my lambda will take a lot of validators, right? Validated takes validators to implement the validation logic. So I will have to pass them, and I pass them explicitly as template parameters and then as forwarding reference to the lambda. My inner lambda will do all the work. So my outer lambda is only there to basically to expose the public interface, but my inner lambda is the one that does the dirty work. So first thing that it has to do is this fancy addition of capturing by forwarding into the lambda. So I'm capturing all the validators, all those functions that are there, and I'm having them now in my inner lambda, but that's not enough. I have validators, but I have to do also perform some action. So what I'm gonna do is most likely validate some arguments, right? It can be anything, whatever it is, because it's a generic function. So I again have to specify generic arguments. Again, an actually parameter pack, because I might be in the need of validating multiple of them. So it's like a, some complex validation scheme. And now we are out of space, I must say. It's not that the insight is very complex. It's actually very simple, but we just need those extra lines. So there are two cases now. Either all the validators validate, and this is basically this line, if all the validators can validate my arguments, and you can see a double parameter pack expansion there. So first I expand the arguments. I'm not forwarding them because that would be basically a death wish for the arguments. I don't want to move them into a validator, but I'm validating them and I'm expanding over the logical or so I can use more validators. If that's true, I will return the optional of my return value, which is constructed from the arguments passed to the lambda. In this case, since I'm passing a password as a string view, or as a conschar even, I will just construct a string as conschar from the conschar and pass it to the optional. If not, well, then no. Then you're returning a null optional. This kind of functions come very often. I have one more example, but not enough time to do it. So I will stop here. It will be a fizz bus, a very similar concept, but doing basically a different pattern with lambdas, a bit more chaining. So if you're interested, talk to me about it. With this one, I would like to thank you. So I will quickly go to the last slide. Yes, that's it. Thank you very much for listening to this talk. I ran out of a little out of time, not that bad. I hope that you, at least got one idea from the talk, or a half of an idea. That's good enough. And thank you very much for listening and for being here.